Welcome to Lecture 6 of Application Development here at Lusaka Goldsmiths University. Today we are covering abstract data types, often abbreviated as ADTs. We will also explore a concept called representation independence, which is closely tied to ADTs. As always, we are guided by our three core software goals: safe from bugs, easy to understand, and ready for change. By the end of this lecture, you will see how ADTs directly support all three of those goals. Let us look at what you are expected to take away from this lecture. First, you should be able to define what an abstract data type is and explain why it matters in software development. Second, you should be able to classify ADT operations into four categories: creators, producers, observers, and mutators. Third, you should be able to design ADTs that are simple, coherent, and adequate for their purpose. Fourth, you should be able to explain representation independence and describe why it makes refactoring safer. And finally, you should be able to write tests for ADTs by partitioning on abstract values, not on internal implementation details. These are the skills we are building today. Let us begin. Before we define ADTs, let us first understand the problem they are solving. Imagine you are building a phone book application. You create a class called PhoneBook, and inside it, you store contacts as an array of strings in a field called people. Now, a client of your class writes code that directly accesses that field. They write something like f.people.length. This works fine, for now. But later, you decide that a map would be more efficient for lookups than an array, so you change the internal representation. The moment you do that, every line of client code that accesses people directly will break. The program no longer compiles. This is called representation exposure. The client has become dependent on how the data is stored internally. Abstract data types solve this by creating a strict separation. They separate how you use a type from how it is stored. Clients interact only through defined operations, never directly with fields. That is the core idea. The term abstraction is part of a family of related ideas that all work together to manage complexity in software. Abstraction itself means hiding low-level details and exposing only a simpler, higher-level idea. You do not show the engine, you show the steering wheel. Modularity means dividing a system into separate components that can be designed, built, and tested independently. Encapsulation means building a protective wall around a module. The module is responsible for its own behavior. Nothing outside can reach in and change its state directly. Information hiding means concealing implementation details so they can change freely without affecting other parts of the system. And separation of concerns means each module is responsible for exactly one feature or one concern. These five concepts are not independent, they reinforce each other, and ADTs are one of the most powerful ways to apply all of them together. You have actually been using abstraction already, just applied to functions rather than data. When we write a function specification, the client only needs to know the preconditions and postconditions. They do not need to know how the function works internally. Local variables inside a function are encapsulated. They are invisible to the outside world. And because of information hiding, the implementer is free to choose any algorithm they like as long as the spec is satisfied. Consider a sort function. The client knows, give me an array of numbers. I will return a sorted array. The client does not know, and does not need to know, whether it uses quicksort, merge sort, or timsort. Today, we are extending these same ideas to data itself. Not just functions, but the types we define. Let us take a brief look at how we arrived at the concept of abstract data types. In the early days of programming, languages only provided built-in types like integers and strings. Users could define functions, but types were fixed by the language. Then, Ole Johan Dahl introduced the similar language, which gave us objects and classes, the foundation of user-defined types. David Parnas formalized the principle of information hiding, arguing that the right way to modularize a system is by hiding design decisions. Tony Hoare contributed to the axiomatic specification of data types, giving us formal tools to reason about them. And then Barbara Liskov and John Guttag, working at MIT, did the seminal work on formally specifying abstract data types. Barbara Liskov was awarded the Turing Award for this work. The Turing Award is the highest honor in computer science, often called the Nobel Prize of Computing. We reference their course material here at Lusaka Goldsmiths University because their work remains one of the clearest treatments of these ideas. So what exactly defines a type? The key insight is this: a type is characterized by the operations you can perform on it, not by how values are stored. Think about a number. What makes something a number? It is something you can add, something you can subtract, something you can compare. Those operations define what a number is. Think about a string. What makes something a string? It is something you can concatenate, something you can index into, something you can measure the length of. In an abstract data type, the user does not worry about how values are stored in memory. They only care about what operations exist and what those operations do. This is the essence of the ADT concept. Define the interface, hide the implementation. ADTs come in two fundamental flavors: mutable and immutable. A mutable type is one where operations can change the object itself. For example, the date type in TypeScript is mutable. If you create a date for January 1st, then call setMonth to change it to April, the same object now reports April when you ask for the month. The object has been modified in place. An immutable type is one where operations never modify the object. Instead, they return new objects. The string type is immutable. If you call to uppercase on the string hello, you get back a new string HELLO. The original string hello is unchanged. Some types come in both forms. Array is mutable. Read-only array is its immutable counterpart. This distinction matters because mutable types are harder to reason about. When an object can change, you have to think about when and how it was changed. Immutable types are simpler. Once created, they never change. Now, let us look at how we classify ADT operations. Every operation on an ADT falls into one of four categories. Creators make new objects of the type. They are the starting point. Producers take existing objects of the type as input and produce new objects of the same type. They do not mutate. Observers take objects of the type and return information about them, usually as a different type. They do not mutate. And mutators change the object itself. They are the only category that modifies existing objects. This classification is not just academic. It tells us exactly how to test an ADT, and it reveals the structure of the type at a glance. Let us look at each category in detail. Creators are operations that bring new objects of the type into existence. There is one important rule. A creator may take values of other types as arguments, but it may not take an existing object of the type being constructed. In TypeScript, creators are usually implemented as constructors using the new keyword. For example, newDate creates a newDate object, or newDate with arguments creates a date for a specific day. Creators can also be static factory methods. Array.of, for example, creates a new array from a list of values. And sometimes a creator is just a literal. An empty array bracket is a creator. Think of creators as the entry point into the ADT. Before you can use any other operation, something had to create the object first. Producers are operations that create new objects of the type, but they require at least one existing object of that type as input. The key difference between creators and producers: creators start from nothing or from other types. Producers work with existing instances. A classic example is string concatenation. The concat method takes two strings and produces a new string. It needs at least one existing string to do its work. Another example is math.max. It takes two numbers and produces a new number, the larger of the two. The critical rule for producers is that they must never mutate their input objects. They take existing values, compute something, and return something new. If a producer modifies its input, That is a bug. It violates the contract. Observers are operations that look inside an object and return information about it, but as a different type. The map type in TypeScript has a size property. It takes a map and returns a number. That is an observer. The get method on a map takes a map and a key and returns a value. Also an observer. The length property on an array takes an array and returns a number. Notice all of these return a different type than the one they operate on. Observers are read-only windows into the abstract value. The critical rule for observers: they must never mutate the object. An observer that secretly modifies its target would be extremely dangerous and hard to debug. Mutators are the operations that change an object in place. The push method on an array adds an element to the end and returns the new length. The array itself has been modified. The sort method rearranges the elements of the array in place. After sort, the array is different from what it was before. The pop method removes the last element and returns it. Again, the array has been modified. Mutators often have a void or undefined return type because the real work is the side effect of changing the object. But not always. Push returns the new length, for example. The rule of thumb is, if an operation might modify the object, classify it as a mutator. Only mutable types have mutators. Immutable types, by definition, have none. Let us apply the classification to a type you use every day. Number. Number is an immutable primitive type in TypeScript. Creators are numeric literals: 0, 142, 3.14. Writing a number literal creates a new number value. Producers are the arithmetic operators: addition, subtraction, multiplication, division, and exponentiation. They take existing numbers and produce new numbers. Observers are the comparison operators: triple equals, not equals, less than, greater than. They take numbers and return booleans, a different type. And mutators, there are none. Numbers are immutable. When you add 2 and 3 to get 5, the numbers 2 and 3 are unchanged. 5 is a brand new value. This is why working with numbers feels so safe. You never have to worry about a number changing behind your back. Now, let us look at array, which is a mutable type. Creators include the array constructor, array literal syntax with square brackets, array.of, and array.from. Producers are operations that return new arrays without modifying the original: concat, slice, map, and filter. Observers are operations that tell you about the array without changing it: length, index access with square brackets, and index of a thing. Mutators are operations that modify the array in place: push, pop, shift, unshift, sort, and reverse. Pay special attention to concat. It is easy to mistake it for a mutator because it feels like it is adding to an array. But concat returns a brand new array. The original arrays are untouched. It is a producer, not a mutator. This is a common source of bugs when developers expect concat to modify the array and it does not. The string type in TypeScript is immutable. Creators are string literals, anything in quotes. You can also use string dot from char code to create a string from character codes. Producers are operations like concat to uppercase, substring, and trim. They take existing strings and return new strings. Observers, really just length. It tells you how many characters are in the string. Mutators, none. Strings in TypeScript cannot be modified after creation. This is an important point that sometimes surprises developers. When you call to uppercase on a string, you are not changing that string. You are creating a new one. If you write const equals hello and then call s dot to uppercase, the variable s still holds hello. You must capture the return value to use the uppercase version. Immutability makes strings predictable and safe to share across your codebase. We have now seen several ADTs. Let us step back and see what they all have in common. An ADT is fully characterized by its operations and their specifications, nothing more. We do not define an array by saying it is a block of memory with elements at fixed offsets. We define it by saying it is something that supports push, pop, length, and index access according to their specifications. Values in an ADT are opaque. Opaque means you cannot see through them. Clients cannot examine or access the internal data directly. They can only interact through the permitted operations. This is the critical difference between an ADT and a plain record or struct. A struct exposes all its fields openly. An ADT hides them completely. When we say a type is abstract, we mean exactly this. The concrete details are hidden. Only the abstract interface is visible. This slide shows a diagram that visualizes what we call the ADT specification firewall. Let me walk you through what it depicts. Imagine two zones separated by a solid wall. On the left side of the wall is the client zone. This is where user code lives. The client sees only one thing, the abstraction. That means the public operations and their specifications, the method names, their parameters, their return types, and what they promise to do. On the right side of the wall is the implementer zone. This is where the implementation lives. The implementer sees the representation, the private fields, the helper methods, and the internal data structures. The wall itself is the specification. It is the only channel of communication between the two sides. The client cannot reach over the wall to grab a field. The implementer can change the entire right side as long as the public specification on the wall remains the same. This decoupling is the whole point. The client and implementer can work independently, each trusting only the specification. Now that we understand what ADTs are, let us talk about how to design them well. The first principle is simplicity. A good ADT should have a small number of simple operations that can be combined in powerful ways. Consider a bad design, an interface with a single method called add and sort and deduplicate. This method tries to do three things at once. It is hard to understand, hard to test, and inflexible. A better design separates those concerns into three operations: add, sort, and deduplicate. Each does one thing clearly. Now, a client who only wants to add does not have to trigger a sort they do not need, and a client who wants to sort without deduplicating can do that too. Simpler operations compose more cleanly. They are also easier to test because you can test each operation in isolation. When designing an ADT, ask yourself, can this operation be broken down? If yes, it probably should be. The second design principle is coherence. Each operation should have a well-defined, unambiguous purpose that makes sense for all valid inputs. Here is a classic bad example. Suppose you add a sum operation to a set. For a set of numbers, this seems reasonable. Add all the numbers together. But what does sum mean for a set of strings? Do you concatenate them? In what order? What about a set of sets of numbers? Do you recursively sum? Do you sum the sizes? The operation breaks down because it does not have a coherent meaning across all the types a set can hold. Operations should work consistently and predictably for every valid input. If you cannot define the behavior clearly for all cases, the operation does not belong in the ADT. Avoid operations that require a long list of special cases. Each special case is a place where the client can be surprised. The third principle is adequacy. Your ADT must provide enough operations for clients to do what they actually need to do. Imagine a string type that only provides a length operation, no char, at no index, of no substring. A client who wants to find a specific character has no way to do it. They know how long the string is, but they cannot see any of the characters. The type is inadequate. Good adequacy means information about the abstract value is extractable conveniently through observers. This does not mean you need to anticipate every possible operation a client might ever want. It means the core use cases must be covered. If clients consistently find themselves needing something that is not in your ADT, that is a signal the design is inadequate. Listen to that signal. The fourth design principle is separation of domains. Do not mix general purpose and domain-specific operations in the same type. Here is an example of the first mistake. Imagine adding a deal cards method to a general purpose array type. Arrays are meant to be general. The concept of dealing cards belongs in a deck type, not an array. Here is the second mistake. Imagine adding a general add method that takes any object to a deck type. A deck is a domain-specific type for playing cards. It should not accept arbitrary objects. That generic add belongs in a general list or collection, not in a deck. The rule is, domain-specific operations belong in domain-specific types. General operations belong in general types. Mixing them creates types that are confusing, hard to maintain, and hard to test. A deck with a generic add operation might accidentally accept a car object, which makes no sense. Now we come to one of the most important concepts in this lecture, representation independence. The principle is stated clearly. The use of an abstract type should be independent of its representation. What this means in practice is that changes to the internal data structure of an ADT should have no effect on any code outside the ADT. Consider an ADT that currently stores its data in a uint16 array. If the implementer later decides to switch to a plain string array, or replaces an array with a map for better performance, sourced, or adds caching fields, none of that should require any changes to client code. The client code is completely insulated from those decisions because the client only ever calls the public operations. This is an enormously powerful property. It means you can optimize, refactor, or completely redesign the internals of a type without touching any of its users. But this only works if the representation is kept private. The moment a client accesses a field directly, that field becomes part of the public contract, and changing it breaks the client. Representation independence is only guaranteed when operations are fully specified. Look at this interface definition for myString. It declares two operations, length and char. The length method has a specification. It returns the number of characters in this string. The char method has a specification. Given an index I in the range from 0 to length -1, it returns the character at that position. These specifications are contracts. They tell clients exactly what to depend on. The client knows that length returns a count of characters. The client knows chart will give them the right character for a valid index. And these specifications tell the implementer what they are free to change. As long as length still returns the character count, and chart still returns the right character, the implementer can store the data in any form they like. Without specifications, clients might rely on undocumented behavior. Then changing the implementation, even without changing the spec, can break code silently. Let us now look at a case study that will carry us through the next several slides. We are designing an ADT called myString. MyString is an immutable sequence of characters. It is a simplified version of the built-in string type. The interface defines three operations. Length returns the number of characters. No parameters needed. It is a property of the string itself. Character takes an index I, where I must be between 0 inclusive and length exclusive, and returns the character at that position as a single character string. Substring takes a start index and an end index, where 0 is less than or equal to start is less than or equal to end, and end is less than or equal to length. It returns a new myString containing the characters from start inclusive to end exclusive. Notice there are no mutator operations. MyString is immutable. Once created, it cannot change. We will now look at two completely different ways to implement this interface. Here is the first implementation, myString1. The representation uses a single private field, a wint16 array called a. A wint16 array stores 16 minus bit unsigned integers, vPostent, which is exactly the range needed to represent Unicode character codes war that. The constructor takes a JavaScript string, allocates a uint16 array of the same length, then copies each character code into the array using charCodeEt. The length method simply returns the length of the array. The chart method retrieves the character code at index I from the array. then converts it back to a character using string dot from char code. The substring method slices the array from start to end, converts those character codes back to a string, and wraps it in a new myString1 object. This is a clean, straightforward implementation. But notice that substring allocates a new array and copies data into it every time it is called. If you call substring on a large string many times, that is a lot of copying. In the next 2 slides, we will see why this matters. This slide shows a memory snapshot diagram. Let me explain what a snapshot diagram is and what this one is telling us. A snapshot diagram is a picture of what is in memory at a particular moment during program execution. Think of it as a photograph of the heap, the region of memory where objects live. In this diagram, we have run 2 lines of code. First, const s equals new myString of the string true. Second, const a equals s dot substring of 1 and 3. On the left side of the diagram, you see the variable s pointing to a myString1 object. That object contains a uint16 array holding 4 values, the character codes for t, r, u, and e. Below that, we'll see the variable t pointing to a completely separate myString1 object. That object has its own uint16 array holding just 2 values, the character codes for r and u. The key observation is this: the 2 objects are completely independent. They do not share any memory. When substring was called, it allocated a brand new array and copied the characters r and u into it. This works correctly, but for long strings with many substring calls, all that copying is expensive. That is what the second representation addresses. Here is the second implementation, myString2. It is an optimized version that avoids the copying problem. This time, the representation has 3 private fields, the same uint16 array called a place, plus 2 numbers called start and end. The insight is this: since myString is immutable, the array will never be modified after creation, so multiple myString objects can safely share the same underlying array. The start and end fields define a window into that shared array. The substring from start inclusive to end exclusive is what this myString object represents. Look at the length method. It returns end minus start. No need to measure the array itself. Look at char@. Instead of just indexing into it directly, it offsets by start first, so index 0 maps to a bracket start. And most importantly, look at substring. It does not copy anything. It creates a new myString2 object that points to the same array, myCowson, with adjusted start and end values. This is significantly faster for substring-heavy code, and it uses less memory. The same data is reused rather than duplicated. This slide shows another memory snapshot diagram, this time for the myString2 implementation. Again, we have run the same 2 lines, const s equals new myString of true, and const t equals s dot substring of 1 and 3. On the left, variable s points to a myString2 object. That object has a uint16 array with the 4 character codes for t, r, u, and e. Its start field is 0 and its end field is 4. On the right, variable t points to a different myString2 object, but look carefully. Ts object does not have its own array. It holds a reference to the same uint16 array that s uses. T's start field is 1, T's end field is 3, so when you ask t for its length, you get 3 minus 1, which is 2. When you ask t for chart of 0, you get the character at position 1 in the shared array, which is r. The 2 objects share one array. No copying happened. This is the power of the optimization. And crucially, the client code does not know or care about any of this. From outside the ADT, s and t behave exactly the same as they did with the first implementation. Let us appreciate what just happened across the last few slides. We changed from representation 1 to representation 2. We added 2 new fields, start and end. We changed how every single method works internally. The constructor changed, length changed, char@ changed, substring changed. That is a substantial internal redesign. And yet, the client code does not change at all. If you had written code using MyString and someone swapped the implementation under the hood from MyString1 to MyString2, your code would still compile. It would still run. It would still produce the same results. You would never know the change happened because you were only ever depending on the specification, not on the internals. This is exactly why ADTs are so important for readiness for change. The abstraction barrier protects you. Changes behind the barrier do not ripple outward. This is the promise of representation independence delivered. Now let us look at a common mistake in TypeScript that breaks representation independence. In TypeScript, unlike some other languages, fields and methods are public by default. If you do not explicitly mark a field as private, it is accessible from outside the class. Consider a phone book class with a field called people declared as an array of strings with no access modifier. A client can now write code that directly accesses that field. They can push directly into the array. They can read elements using index syntax. This seems harmless at first, but now the phone book's internal structure is part of its public contract, even though you never intended it to be. If you decide to change people from an array to a map for faster name lookups, every line of client code that used the array interface breaks immediately. The fix is simple and non-negotiable. Always mark your representation fields private. Private means the field cannot be accessed from outside the class. Clients must go through your defined operations. That is the firewall. Let us look at how the ADT concepts map onto TypeScript language constructs. An abstract data type can be realized as a class, like the date class, or as an interface plus one or more implementing classes, like the iterable interface and array, or as an enum for small fixed sets of values. Creator operations map to constructors using the new keyword, to static factory methods like array.of, or to constants like number.positive on infinity. Observer operations map to instance methods like string.char@, or to static utility methods like object.entries. Producer operations map to instance methods like string.trim, or to static utility methods like math.floor. Mutator operations map to instance methods like array.push, or to static methods like object.assign. And the representation, the private data, maps to private fields in the class. TypeScript gives us all the tools we need to implement ADTs correctly. We just have to use them intentionally. Now let us talk about how to test an ADT. The core strategy is write tests for each operation. But here is the challenge. ADT operations are interdependent. You cannot test a creator or a mutator in isolation. To verify that a creator worked, you need to call an observer. And to test an observer, you need an object that was created by a creator. This means every ADT test involves at least two operations working together. Look at the example for testing push, which is a mutator. First, we use a creator, the empty array literal. Then we call push to add the value 42. Then we use observers, length, and index access to verify that the push worked correctly. Notice that we never directly inspect the internal array structure. We only check through the public operations. This is correct testing for an ADT. The tests are independent of the representation. When designing test cases for an ADT, we partition the input space. But there is an important rule. Partitions must be based on abstract values, not on internal representation. For MyString, here is how we think about partitions. For the length operation, we partition based on string length, 0 characters, 1 character, or more than 1 character. For char@, we partition on the index I0, somewhere in the middle, or the last valid index. We also partition on how the MyString was created directly through the constructor or produced by a previous substring call. For substring, we partition on the start index. Is it 0, somewhere in the middle, or at the end? We partition on the end index similarly. And we partition on whether end minus start is 0 or positive. For mutable ADTs, we add another dimension. Has the object been mutated? An object that has been mutated may behave differently from a freshly created one, and bugs often hide in that difference. The goal is to cover combinations of these partitions so that every meaningful scenario is exercised. Let us look at some concrete test cases for myString. The first test covers a string of length greater than 1 and tests char at both the first and last positions. It creates the string yes, verifies the length is 3, checks that char at 0 returns y, and char at 2 returns s. The second test covers the edge case of an empty string and also exercises substring on an empty string. It creates an empty string, verifies length is 0, then takes a 0-length substring starting and ending at 0, and verifies that substring also has length 0. The third test covers a string that was produced by a previous substring call and tests char on that result. It creates the string hello, takes a substring from index 1 to 2, which should give just the character a, and then verifies the length is 1, and char at 0 returns e. Notice every test uses only public operations. No test reaches into the internal fields. These tests will work correctly whether the implementation is myString1 or myString2. That is the hallmark of a well-written ADT test. There is a common testing mistake that is worth calling out explicitly. When you have two myString objects that you believe contain the same characters, you might be tempted to compare them directly using assert.strict equal, which uses triple equals under the hood. But triple equals on objects checks identity, not value. It asks, are these the exact same object in memory? Two different myString objects constructed from the same string are two different objects. They occupy different spots in memory. Triple equals returns false, even though they represent the same sequence of characters. Unless your ADT explicitly defines an equality operation, a method that compares two instances by their abstract value, you cannot use direct equality to verify results. Instead, use observers. Compare their lengths, compare char, at each position, build up your verification from the operations the ADT provides. This is not a limitation. It is the correct approach. Your tests are specification-based, not implementation-based. Let us bring it all together and return to our three core software goals. Safe from bugs. An ADT provides a well-defined contract between the client and the implementer. The client knows exactly what operations exist and what they promise to do. The implementer knows exactly what they are obligated to deliver. This clarity prevents entire classes of bugs. Easy to understand, an ADT hides its implementation details behind a small, clean set of operations. A programmer using an ADT does not need to understand linked lists, hash tables, or bit manipulation. They only need to understand push, pop, and length. This reduces cognitive load enormously. Ready for change. Representation independence means the internal structure of a type can be completely overhauled without touching client code. This is invaluable in real-world software, where requirements change and performance improvements are needed. ADTs are not just a theoretical concept. They are a fundamental tool for writing software that lasts. Let us close with a summary of the key ideas from this lecture. ADTs are characterized by their operations, not by their data structure. The interface defines the type. Every ADT operation is a creator, a producer, an observer, or a mutator. Knowing which category an operation belongs to tells you whether it mutates, whether it returns a new value, and how to test it. Good ADT design follows four principles: simplicity, coherence, adequacy, and separation of domains. Always keep the representation private. The private keyword is not just a suggestion, it is the mechanism that enforces the specification firewall. When testing, partition on abstract values. Use observers to verify results. Never access internal fields from tests. And representation independence is the payoff for all of this discipline. Change the internals freely whenever you need to. Your clients will never know. That is Lecture 6. Thank you.